Now we have Sandor Beregi, who's going to tell us about learning measured bifurcation diagrams with UDEs. Take it away.
Okay, thank you very much for the kind introduction. So I'm Sandor Beregi from the University of Bristol, and as said, I'm going to talk about learning measured bifurcation diagrams with UDEs, so universal differential equations. So basically, this research I'm going to present here is mostly on using data-driven models on nonlinear dynamical systems, which is linked to a project on creating digital twins, which are essentially data-driven adaptable virtual counterparts for real-world or physical systems. And what I found that universal differential equation models are especially good candidates as digital twins because they basically allow for having a physics-based core they allow for incorporating some of our insight into these models, but by adding a machine learned structure to the physics-based part, we can compensate for the modeling errors and potentially reach a very high accuracy. This is all very promising. And I would like to use these models for nonlinear dynamical systems, which is basically the broader area I do research in. So that's my background, which are essentially focused on systems undergoing so-called self-excited vibrations. And the main complexity with these kind of systems that they are most typically lead to varying parameter problems that usually gives an additional complexity to the training procedure. And I will present one specific application related to an engineering oriented field, aeroelastic flutter, for which I carried out a few numerical simulations, but I also trained the models on experimental data. Okay, but before that, I just would like to give a short introduction on what nonlinear systems actually are and what are the problems I'm interested in. So basically, nonlinear dynamical systems can be considered as differential equations in the following form, like we have a derivative of a state variable equal to some nonlinear function of the state variable and some system parameters. I'm considering here ordinary differential equations, but one can also take into account or study more complex or more exotic type of differential equations, and the equations can be either autonomous or non-autonomous if we have an explicit time dependence in the equations. The important point is that in the focus of my investigations are systems which have periodic solutions, and one very common example is the Hopf bifurcation, which is a feature in autonomous differential equations. And basically, these two bifurcation diagrams in the bottom of my slide show the typical characteristics of the two basic cases of the Hopf bifurcation, the supercritical and the subcritical one. So essentially, in bifurcation diagrams, we typically show the steady state solutions of the system with information about their stability. So in this case, I highlighted the stable and unstable solutions with different colors. So for example, what happens here, that in the supercritical case, in the horizontal axis, I'm showing a chosen parameter, which is referred to as a bifurcation parameter, whereas in the vertical axis, in case of periodic solutions, it's typical to show some sort of a norm related to the vibration amplitude. So basically here, in the horizontal axis, we have equilibria, which loses its stability at a certain value of the parameter lambda. And what happens here at the Hopf bifurcation, that at the stability boundary, there is a stable branch of periodic solutions emerging from this point. And then this is the supercritical Hopf bifurcation, whereas in the case of the subcritical bifurcation, a similar thing happens, but in this case, the branch of periodic solutions is an unstable branch. But what very commonly happens that later on, this unstable branch undergoes a so-called saddle node bifurcation and becomes stable again. And so basically the reason I like these diagrams and why these tell us often more information than like a simple numerical simulation would tell is because using essentially the information of the steady state solutions and their stability, we can also infer what the transient of the system would look like, and starting with different initial conditions from different regions of the phase space of the system, as these arrows basically indicate, we can tell where the solution would converge to. And from this point of view, probably the most interesting region is this one in the case of the subcritical bifurcation, when we have a so-called bistable parameter region where we have a coexisting stable equilibrium and a stable large amplitude solution. And then basically the initial condition is going to decide whether we will see the equilibrium or a large amplitude oscillation in the longer term, or as steady state behavior, which are obviously two entirely different type of behavior. Now, the important thing is that in this case, the unstable periodic solutions play an important role because they essentially are attached to the boundary between the domains of attraction of the two stable solutions. So that's why it's actually also important to characterize this, which can be a bit challenging because this solution never directly appears in experiments since they are unstable. But we have a control-based technique to trace them, so it's actually possible to get information of them in measurements. So as I mentioned earlier, and I hope that I could make this a little bit more clear, why these are actually varying parameter problems. And on the other hand, these systems are relevant in several engineering systems. I just wrote a few examples. I hope the video is going to start. One is the example I'm going to show some numerical results of is aeroelastic flutter, which is basically the self-excited vibrations of aerofoils in airstream. The other one is another area which I did a lot of research in, is wheel-shimmy, which is basically the self-excited vibration of rubber tires. Now, as you can see, these vibrations are relevant because they can either cause some mild discomfort, but in some cases, if we are unlucky, then they may even lead to accidents, which is obviously dangerous. So we would like to avoid them. Okay, so after this introduction, I would like to move on and introduce the modeling concept I have for these types of systems. So my assumption is that we have an experiment or a system we are observing, which has these kind of periodic solutions. So for example, a subcritical Hopf bifurcation, as you can see in this example with the bifurcation diagram. And usually the case is with an engineering system that one already has some sort of a knowledge or insight into how the system actually works. Therefore, it's usually possible to come up with a good physics-based model, which at least in a qualitative sense describes how the system behaves. But usually the case is that that model is never 100% accurate. So there's always going to be some error due to the neglections and simplifications one has to make during the modeling procedure when compared to measurement data. So that's why I'm adding a universal approximator to the physics-based part and using a universal differential equation model to reach a higher level of quantitative accuracy when compared to measurement data. So if we take a look at what our model looks like in terms of equations, then from the point of view of an experiment, at least to me, it makes sense to divide the system to an accessible and the hidden part. Basically, the accessible part meaning all the state variables and everything about the system which we can have, which we can measure. And but as I said earlier, there are always going to be some neglections. So it's fairly safe to assume that there is always going to be a hidden part of the dynamics which we cannot model. So essentially what we do is that I consider a physics-based model for the accessible part and try to fine-tune it to make it as good as possible, and then add machine learnable structure to compensate for the error between the measurement data and the smaller order physics-based model. So basically, the two types of machine learned structures I'm considering for this problem is neural networks, for which I use the diffeq flux package in Julia. So in this case, basically the model error and the objective function is calculated from the error in the predicted trajectories compared to the measured ones, whereas in the other case, when I consider Gaussian processes, it was a little bit different, because in this case, the model was fitted directly to the right-hand side of the differential equations, which means I had to use acceleration data. On the other hand, Gaussian processes were more useful in the cases when there was some noise in the system, because they are essentially have a natural way of considering process noise in the model. Okay, so in the following slides, I just would like to going to present my results on the model of aeroelastic flutter, starting with the numerical simulations. So in this case, I consider the 2+1 degrees of freedom model of flutter as the underlying model of an experiment, or the ground truth, if you would like, where basically the two physical degrees of freedom of this aerofoil here, the heave and the pitch motion, was considered as the accessible part of the model, whereas the model had a non-physical degree of freedom related to the aerodynamic effects, which are considered as the hidden part of the model. So basically what I did is to created a 2 degrees of freedom physics-based model using just the accessible part, the heave and the pitch motion, and added a machine learned structure to compensate for the model error. Now, if I consider the simplest possible case, when I had a deterministic system, then actually this kind of model with a neural network as a universal approximator turned out to work really well. So as you can see, basically, I was able to train the model to replicate what the underlying model does, and what the measured or in this case the simulated periodic solutions were. But I also added the bifurcation diagram of the pure physics-based model, just to highlight that in this case, the difference between the behavior of the ground truth model and the physics-based core of the universal differential equation model wasn't that large. So in this case, I really just compensated for a small error in the model. So we can kind of say that, okay, this worked really well, but this was probably not a very realistic example. So I just tried to increase the complexity a little bit by considering process noise. And in this case, I use Gaussian process as the universal approximator, which still worked quite well. Basically, the important conclusion in this case was that quite predictably, the signal to noise ratio was important. which unfortunately also kind of limited the amount of noise one could actually consider in the model, because the acceleration data was more prone to noise excitation than the trajectories in case of the neural network-based models. This is basically the reason why I use the neural network-based model when I try to train the model for actual measurement data taken from the physical experiment. You can see the right-hand side of my slide. Basically preconditioning the measurement data and using it as a quasi-deterministic training data. And as you can see, basically it was possible to train a universal differential equation model which could replicate the measured bifurcation diagram. So we could say that this is a relatively nice result. Unfortunately, we found that that solution was quite sensitive to the initial conditions of the training algorithm. So actually, it very often converged to a local minimum instead of a global one. And in this case, as you can see, the characterization of the system behavior is, well, it's suboptimal, as they say. So basically, this raised the question: how can we actually improve the robustness of the training procedure? And an obvious thing, or at least it seemed to be obvious to me, that the current training framework or the training framework I used previously didn't really utilize the information that we are actually dealing with systems with periodic solutions. It was just a result that kind of indirectly was in there, but there was no direct information about this. So what I tried to do, that instead of using an initial value problem solver, as is the case with the diffeq flux package, I tried to do something similar with a boundary value problem solver. And I can see I don't have too much time, so I just try to show the results and wrap this up quickly. But basically, I have a very simple example of this when I'm using the technique of numerical collocation. And once again, I'm just comparing the identified periodic solution to the measured data, or in this case, it's actually generated by a numerical model. So basically what I do in this case, that I'm just trying to learn the damping parameter in the deafening oscillator model, whereas the other system parameters I fixed. And this could be done with relatively good accuracy, finding a solution that is very close to the original value. And as you can see, the identified model fits really well to the measurement data. But this is really just for trying whether this type of concept could work. It's very early days, because I, of course, just identified a simple parameter, not really trained a neural network or any more complicated model, but that would be the goal in this case. So to summarize these things and my presentation, basically this is very much an exploratory study, mostly to find out the potential of universal differential equation models for nonlinear dynamical systems. And basically one of the main conclusions I could draw from my results is that it very much depends on the complexity of the problem. So if the difference between what the physics-based model can do and what we see in the experiment is small, then usually the model these models tend to work well. If the measured behavior is more complex, then we may have further difficulties, and the training procedure is often less robust. So and basically my idea and concept to improve this and tailor this to work well with bifurcation diagrams would be to change for a boundary value problem solver in the algorithm. Thanks very much for your attention, and I would like to draw your attention to a preprint that's available on arXiv. So if you found it interesting, then please have a look at that. Thanks very much.